Mba633 instructional video prepared by Professor Ahmed Tata, School of Management, George Mason University. In this segment, we will discuss some building blocks associated with simple linear regression that will help us hopefully understand what exactly is going on in the process of doing simple linear regression using a data set. And hopefully these building blocks will provide a structure to let us understand the output from Excel when one uses that software to carry out simple linear regression. So the example we will use is the same one that we had for our first video clip. So we have two variables here, square footage and price. So we have a data set consisting of 20 houses, their prices and square footage, and this is simple linear regression. And so we have one dependent variable, you always have one dependent variable, in this case price, and we have one independent variable, which is square footage. So we are trying to explain the variation in price using square footage. Since we have one independent variable, it's a simple regression, and we are hypothesizing a linear relationship between these two variables. That's the simplest type of relationship one can have. Hence, we are carrying out simple linear regression. So let's see what these conceptual building blocks are. What's actually going on conceptually when we are doing simple linear regression? So let's look at the scattergram. So in this little graph over here, I have plotted the XY values for each of the 20 houses. So each dot represents one house. Its x-axis represents the square footage and the y-axis represents the corresponding price. So there are 20 dots. And the line that you see is the linear best fit line through these data points. For now, never mind how we got that line, but let's try to construct some of the basic building blocks as to what's going on when we're doing simple linear regression. So first of all, we have two variables here. The dependent variable price we represent by the letter y. The independent variable square footage we represent by the letter x. And the first relationship we hypothesize is y is equal to beta 0 plus beta 1 x plus epsilon. Now if you forget about the epsilon for just a second, you can see that y equal to beta 0 plus beta 1 x is the equation of a straight line. So we are hypothesizing that housing price is equal to some intercept plus a slope times the value of the square footage. But I know that this straight line will not be a perfect fit through the data points. Hence this error term. So sometimes the prices will be above what we have estimated, sometimes they will be below. Now, very important aspect of linear regression is an assumption made about this error term. So when we do linear regression, we assume that this error term is normally distributed with a mean of 0. There are some important implications. The first implication is sometimes the data points will be above the fitted line, sometimes they will be below. They will not all be on one side or the other. And that follows from the fact that the mean of the error term is 0. So sometimes the error term is positive, sometimes it's negative. In this case, for example, this particular house, you can see that the error term is negative. The error term is simply the difference between the actual value of the price and what the fitted line says the price ought to be. Okay. Now there's another implication of the normal distribution. You know from the shape of the normal distribution, which is a bell-shaped curve, that the values are not uniformly distributed across a range. When you have a normal distribution, most of the values are bunched around the middle. Okay, you remember the empirical rule that 68% of values are within one standard deviation of the mean, 95% within two standard deviations, and so forth. Physically, what that means is if you look around this fitted line on either side of the line, most of the data points will be bunched close around the line. So they will not be evenly scattered about the line. Okay, so it's not equally likely for a data point to be far away from the fitted line as it is to be close to it. Okay, so most of the data points will be bunched about on either side of the fitted line. Once in a while, you will see a few stray points that are far away from the fitted line, and that follows from the fact, the assumption of the normally distributed error terms. Okay, so now let's see what that implies. So this implies that the expected value of y, if I give you a value of square footage, what would I expect the value of housing price, house price to be. Since the expected value of the error term is 0, the expected value of y would simply be beta 0 plus beta 1x. So this is the equation that I'm really trying to find out. This is the straight line that I'm trying to determine. And all I have to do to determine this line is to find out what beta 0 is, the intercept, and what the slope beta 1 is. And now here we have a slight problem, because in order to get beta 1 and beta 0 perfectly, I need to look at all houses, all the millions and millions of houses. So I need to look at the population of houses, and for each house I need to extract its square footage and its price, and based on that compute the slope and the intercept. So in other words, the important thing to remember here is that beta 1 and beta 0, okay, are the slope and intercept of a line that is supposed to fit the population. Obviously, I cannot deal with millions and millions of houses. So what do I do? Whenever I do regression, I always use sample data. So in our case, you remember, we had a sample data set with 20 houses only, not the millions and millions of houses that I'm actually trying to fit. So what do? I take the 20 houses that I have, so I take sample data and I fit a straight line through it. This straight line that you're seeing here in this scattergram is a straight line fitted through 20 houses, not the millions of houses that I really would like to fit. Okay, so the slope that I get from this 20 houses is represented, the equation that I get by fitting a straight line through these 20 houses is represented using slightly different symbols. You see, we wrote y hat, which is the fitted value of y, using the data set, is equal to b0 plus b1x. Notice we did not use beta, the symbols beta anymore. So this is what is called the estimated equation. What is the significance of that? The significance is whatever I estimated, the estimated intercept b0 is my best guess of the true intercept beta 0, and the slope b1 that I got through these 20 houses is my best estimate of the true slope for the population. So we have a typical case here of a situation where I want population parameters. I really want to estimate beta 0 plus beta 1, but because I cannot look at the population of all houses, I look at a subset, I look at a sample of houses and do my regression using that. So I get b0 and b1, which are intercept and slope for samples. So I have sample data, the estimated regression. So whenever you use sample data, a data set, to compute a regression equation using Excel or whatever other piece of software, you are really estimating a sample statistic, which is an estimate of the true population parameter that you really wanted to estimate in the first place. Okay. So you remember from hypothesis testing, confidence intervals, and all of the inferencing that we have done before, anytime you estimate population parameters from a sample, you are doing inferencing, and that involves uncertainty. So the upshot of all of this is when you do simple linear regression, or for that matter multiple regression in Excel, Excel will give you this equation, the fitted equation. That's a very small part of the output. That's an important part of the output, but it's a small part of the output. The bulk of the output from Excel really is there to let you judge the quality of this inferencing. In other words, the fitted equation that Excel gives you, how reliable is it, how good is it, how good an estimate of the true intercept and the true slope is it. So all the diagnostics, 90% of the output from Excel associated with a regression is just diagnostics to tell you how good of an inferencing you've done. So you've looked at your sample data, and Excel has fitted a straight line through your sample data, given you an intercept, given you a slope. How good is it? Should you be relying on it confidently as a good estimate of beta 0 and beta 1? Okay. Now one can show that for the sample data that the fitted line must pass through X bar and Y bar. Well, you can prove that mathematically. So in our case, we have a set of 20 houses. You can prove mathematically that the best fit line has to go through X bar and Y bar, middle of X and the middle of Y. And then based on that knowledge, you can also prove using simple basic calculus that B1, the slope of the best fit line, is given by this closed form expression sigma of xi minus x bar times yi minus y bar. The main thing to see here is all these values are known. Okay, so these this slope and the intercept that Excel computes is based on what is called ordinary least squares. Okay, the method that how does it know does it have that it has the best fit line? We know that the line has to go through x bar, y bar, the middle. So you think conceptually as if you got your pivot at this middle point and you're tilting the line. It's like you're making it more steep and less steep. And as you do so, the sum of the squared errors, yi minus yi hat. So what the difference between the actual value of the price and the predicted value of the price based on the line, that's the error term. You square it and you sum that up for all the data points. So you will get a sum of squares. This is called this is the sum of squares, and you keep tilting the line until this sum is minimized. Okay, so ordinary least squares. So the best fit line will have a slope. I know it's going to pass through the middle, x bar, y bar. It will have a slope that minimizes this sum of squares, squared errors. So sum of squared errors is minimized, and when that happens, that's what's the best fit line, and you can show mathematically that the slope of the best fit line is given by this equation for B1. Okay, so that's how Excel actually goes about computing, and let me show you how one would do that. Maybe since we are running out of time for this segment, I will show you how to actually use Excel to compute the best fit line and to interpret its diagnostics in the next video segment. So we will use these conceptual building blocks. Remember that we are actually, what we would like to find is the true intercept and the true slope for the line that predicts price as a function of square footage, for using all, and this should apply for all houses. So this equation is for the population of all houses. Unfortunately, since I cannot deal with the entire population of all the houses, I work with a sample, and the regression equation that I compute using Excel will give me an intercept and a slope, which are sample estimates of the population parameters. Okay, so the intercept that I get from Excel is an estimate of the true intercept. The slope that I get from Excel is an estimate of the true slope of the regression line. And the diagnostics from Excel will help me understand how good of an inference I have, how good these numbers are that I got from the sample. So in the next segment, video segment, we'll actually run the regression and see how Excel generates the output for the equation, as well as we'll try and interpret the diagnostics.